Okay, I'm gonna have to use the podium microphone. I don't like standing at the podium, though. I like walking around. Okay, so let's get started. Good morning, chemists. Thank you for joining me on this snowy day. I was worried I wasn't gonna make it, but I'm here. So plan is today is to continue on with chapter 13. I don't think we will finish it today. We'll get through most of it, but this is a calculators out kind of day. So we left off on this slide 30 of the chapter 13 slides. Yes, calculators out. So this is the last part of the section where we are exploring gases dissolved in solution. Oh, I can't move around. I have to stand in one place. Calculating gases dissolved in solution. So this is nitrogen gas dissolved in water. And so we should understand that we are using Henry's law here, where the solubility of our gas, so in this case it is not CO2, it is nitrogen. Our previous example was CO2, and I just copied it. So this is N2 gas. The solubility of nitrogen dissolved in gas is proportional to a constant, so Henry's law, constant, which is given in this question, times the partial pressure of nitrogen. That's the important part here. So it's the partial pressure of nitrogen that this solution is in contact with. So this question is asking how many grams of nitrogen is dissolved in 50 liters of solution in contact with air that's pressurized to a total of 5 atmospheres. Does this pressure, when we plug everything in here, is this number going to be 5 atmospheres? No, because it's 5 atmospheres, the partial pressure of nitrogen. No, it's not. The other piece of information given in this question is that the mole fraction of nitrogen in air is 80%. Only 80% of the particles in air are actually nitrogen. So first we need to calculate what is the partial pressure, what is the contribution of nitrogen in this air sample, and that's going to be 80% of that total pressure that's given in this question. So I started the work here that the partial pressure of nitrogen is this total pressure, so the full equation here would be partial pressure of nitrogen is equal to the total pressure given in the question, but times the mole fraction of nitrogen in this sample. So we see that nitrogen is contributing 4 atmospheres of that total pressure. So now at this point, it's plug and chug. So solubility of nitrogen is equal to Henry's law constant, so 6.4 times 10 to the negative 4 molarity, ATM, and then we multiply by this 4 atmospheres of nitrogen that we just calculated. And so when we plug those numbers in, we get that the solubility of nitrogen or the concentration of nitrogen in this sample is 0.00256 molarity. Is that our answer? No, because this question is asking how many grams of nitrogen is dissolved in this 50-liter sample. So all of what we just did is the new stuff using Henry's law. Now to finish this question is just Chem 1210 review and doing molarity conversions. So we have the solubility of nitrogen in molarity. What is the unit of molarity? What does big M mean? Moles per liter. Yes, moles per liter. So what this concentration means is that there is 0.00256 moles of nitrogen per every 1 liter of solution. Do we have a liter of solution? Nuh-uh. We have 50 liters of solution. So now it's a little bit of dimensional analysis. So we have 50 liters of solution. Now I'm going to go ahead and use that molarity that I just calculated here, and using it as a conversion factor, for every 1 liter, there's 0.00256 moles of nitrogen. So yes, we are multiplying by molarity, but if you look at the units here, you'll know that we are multiplying by molarity. So if we plug this into our calculator, we will get moles of nitrogen come out, but we don't want that. We want grams. So how do we convert from moles to grams? What? property do we use? Molar mass, yes. So I even give you the molar mass of nitrogen, where 1 mole of nitrogen gas is 28 grams-ish. All right, and so you get that, and you get that there is 3.6 grams of nitrogen dissolved in this sample. So this last step of us using the molarity, the volume given, and the molar mass is just review of Chem 1210 stuff. The new thing was Henry's Law. All right. Okay, so we're done with this part of the chapter, so we're going to move on to the part that really will utilize and push your boundaries of using your calculator, and that is expressing different concentrations. So actually that previous question was a perfect kind of segue where we used molarity, that concentration. We explored molarity a lot in Chemistry 1210, us understanding that it's the unit of molarity is moles of solution, moles of the solute, the thing that's dissolved, divided by the liters of that solution. So that is molarity. So we're going to expand on that and look at other units of concentration to express how concentrated something is or how dilute something is. All right, so we used molarity before. Now let's look at other concentrations. So the first one we'll look at is mass percentage. And so I have starred up in the corner there an important note, an important idea that's going to come up and something you should be aware of when doing these calculations. When I talk about a solution, I'm referring to both the solute and solvent that I'm combining. So make sure you take note of that when we do these calculations, because note here, if we want to calculate the mass percentage of A, say we dissolve compound A in water, to calculate the mass percent, we just take the mass of A that's in that solution and divide by the total mass of that solution. So let's say like we dissolve 5 grams of A with 50 grams of water. All right, we combine those two things. 5 grams, it's going to go on the in the numerator because that's the mass of A. But what is the total mass of the solution? Is it 50 grams? It's 55 grams. Yes, because remember, solution means solute and solvent. So this total mass is the mass of both the solute and solvent that we combined. So that's how you would get that mass percentage. Of course, you have to multiply by 100 at that point to actually make it a percentage. And so what's related to mass percentage is also some other terms you might have heard of, parts per million and parts per billion. We calculate it the same. It's just once we get that fraction, what is the fraction of A over the total mass of the solution, instead of multiplying by 100 to get mass percentage, we multiply by times 10 to the 6 to get parts per million, or by times 10 to the 9 to get parts per billion. So I like to kind of group all of these concentrations together because you calculate them all the same. You start with the fraction, but then you multiply by the appropriate multiplier to get either percent, parts per million, or parts per billion. So let's calculate the mass percentage of CO2 in an air sample. All right, so I give you the mass of CO2 and the mass of the air sample. So that's 75 grams. This is, in fact, our solution that's going to go into the denominator. So my strategy here is let's calculate the fraction first, because this question's asking, okay, give me the percentage, parts per million, and parts per billion. And so for each of those, I'm going to start with the fraction and then just multiply by the appropriate multiplier. So to get the mass fraction of CO2, we do mass of CO2 over, I guess, the mass of the air sample, and so that's our solution. And so in this case, it's 0.032 or 0.032 grams of CO2 over 75 grams of that air sample. And so what we get here is a tiny number. Did I write it down? No, I didn't. So this number is, I think, something like 0.00 0.043. And so that's the fraction. So in order to get a percentage, we multiply by 100, and so we get that this sample is 0.043% CO2. So I'm starting with this fraction that I just calculated. To get to parts per billion, we multiply by times, or 10 to the 6th, so we're multiplying by a million, essentially. And so we get that this air sample is 430 parts per million CO2. So if we were to count all of the particles, if we would count 1 million particles, 430 of them would be CO2 particles, or I guess the gram amount. And then lastly, to get to parts per billion, we do times 10 to the 9 and get a very large number, 4.3 times 10 to the 5 parts per billion CO2. All right. And so that's kind of the thought process there. If you start with the mass fraction first and then multiply by either 100, 1 million, or 1 billion, that's how we go from percent parts per million, parts per billion there. And so the reason why you might want to use these different concentration units, why we use these different multipliers, is that one of these answers looks the best to our eyes. If we had to read like a research paper with a bunch of different concentrations, which of CO2, like in air, which unit here of the three is the best to look at? Parts per, which one? Million, yeah, parts per million, a 400 number. Yeah, that's an easy number to read and make comparisons if we're looking at a lot of different air samples. If we're looking at really small numbers or really large numbers, they're not as nice to look at. So if we were studying CO2 concentration in air, parts per million would probably be the best way to report that information. All right, so that is mass percentage. So we take mass of our solute and divide that by the total mass of the solution. Remember, that means mass of solute and solvent. All right, so that's one of the types of concentrations. Let's look at some other ones. The first one here is mole fraction. We already talked about mole fraction previously in 1210 when we studied gases, where it's similar to mass percentage, where it's, you know, the solute over the solution. But in this case, we're just working with moles instead of masses like we did in mass percentage. So mole fraction is moles of A over total moles of all components in our solution. So remember, this is solution, so this means we need to include the solute moles, so the moles of solute, plus the moles of solvent. We have to include both, all right? So you have to, you know, calculate the moles of water and the moles of solute that you add, and that will be in your denominator here. Right? So that's review. I think we'll do an example of one of those, but that one is review. From chapter 4, also review molarity, moles of solute over liters of solution. Again, solution means the solvent and solute. So when you think about liters of solution, it's the volume created when you combine that solute and solvent. And so the new one that we are going to be studying in the next slides is molality. So molality looks kind of weird, very similar to molarity, but it's very different. Note the lettering we use. Molality has the symbol little m. All right, so if I write, you know, something is 1 molarity with a big M versus 1 molality with a little m, that's not a mistake. The little m means molality, which means something different here, where molality is moles of solute again, but this time it's kilograms, so weight of solvent, just the solvent. All right, so in molarity, we included liters or volume of both the solute and solvent, but here in molality, we are just looking at kilograms of solvent. That's in the denominator. All right, so let's explore these concentrations. Essentially, just let the unit do its work to help us understand and convert to new units that we want to get to. All right, so the density of a 5% by mass potassium phosphate aqueous solution is 1.043 grams per centimeter cubed. And there's the molar mass of the solute. So this is K3PO4. All right. What is the molality of this solution? All right. Again, let's let the units do the work for us. Okay. So if this is a aqueous solution, what's our solvent? What is it? Water, yes, it is water. So I didn't denote that, I didn't tell you explicitly that the solvent is water, but you should know that because I said aqueous solution. So that means K3PO4 is the solute, and then H2O, water, is our solvent in this case, all right? Okay, so the strategy here, because we're given mass percentage, it's 5% by mass, the solute. Let's assume we have 100 grams of sample, and that's going to help us a lot here, all right? Because if we have 100 grams of sample and this is a 5% solution, that means if I have 100 grams of sample, 5 grams of it, I'll do sig figs, 5.00 grams of it is my salt, so K3PO4. Then how can we determine how much water we have? It's the rest of the sample, right? If this is a 100-gram sample or solution, 5 grams of it is going to be the salt, and 95 grams of it is going to be water, H2O. All right, so do you see how I did that? All right, this idea right here is where a lot of students get stuck on because we have to kind of make an assumption. We need to start with some amount of stuff. And then using these numbers, we can calculate molality. So let's remind ourselves, what is the unit of molality? So just scroll back to the other slide. What is the unit? Moles of what? Solute over what? Kilograms of solvent. Okay, do we have one of these already? Yeah, basically. We have the denominator, right? We know how many kilograms of solvent we have. We have 95 grams of water. So we actually already know that denominator. It's going to be 0.095 kilograms of water in this 100-gram sample. All right, so how do you think we'll get the numerator? We'll just use the other piece. Yeah, I know that I have 5 grams of solute, so we'll just use the molar mass that was given or that we can calculate ourselves, convert grams of that solute to moles of that solute, and that's what's going to go in the denominator. So let's go ahead and get that using molar mass. So we're going to take that 5 grams of salt, K3PO4, times molar mass here, and so molar mass has a unit of grams per mole, so that 212 is going to go in the denominator, and then 1 mole will go up top, so we're dividing by molar mass, and we get something. I forgot my I'm bad and forgot my calculator. This was a bad day for me to forget my calculator. So 5 divided by 2.21227. Okay, there is 0.02355. I'm just going to use some extra sig figs. Moles of solute present in this 100-gram sample, and this is going to be our numerator. So I can go ahead and now finish the calculation where this number we just calculated goes in the numerator, 0.02355 moles of salt, K3PO4, over 0.095 kilograms of H2O, and we get an answer of 0.248 molality, small m, of this solution, right? So when given mass percentage and you want to convert to a different concentration unit, the best thing to do is start with an amount of solution, and the easiest thing to do is just assume we have 100 grams of that solution, so we get some nice numbers to work with to do our mole conversions or what have you. Okay, so let's do another one. Oh, it's the same one. It's actually the same, is this the same? Yes, okay, so here. I thought this was the exact same question, but it's a little bit different. So this is still the 5% by mass K3PO4 solution. You might be wondering, you know, in the previous question, why did I give you density? Why did I give the density of this solution when we didn't need it in this example where we converted mass percentage to molality? So let's do this question. It's the same information is given. The density of 5% mass solution is 1.043 grams per centimeter cubed. There's the molarity, but this time we're calculating the molarity of the solution. Molarity, big M, big M. So this is, in fact, a different question. So let's remind ourselves, what is the unit of molarity? Moles of solute, but this time it's over volume of the solution. Solution, yes, solution. All right, so we're going to do the same exact thing where we are going to assume we have 100 grams of solution. So that means there's 5 grams of the salts, K3PO4 present, and there's 95 grams of water, right? But this one's a little bit different. Okay, so we already have this numerator part, moles of solute. We got that in the previous question where we used molar mass, and we calculated that there is 0.02355 moles of K3PO4. All right, we have that numerator. But in the denominator, we have to do something a little bit special to get the volume of that solution. I know how much mass of solution I have. I have 100 grams of sample. So what piece of information in this question can we use to go from grams to volume? It's the density, yeah, so now we're going to use density when converting to molarity, and that's what's going to oftentimes happen. In order to calculate molarity of a solution, we have to use the density in some way. So we are going to use this density number finally. So the volume of the solution, in order to use density, we need the mass of the solution. So if we have 100 grams of solution, we can use this density value. So note that this number, I'm not using 95 because that's just the mass of water. We want to use the mass of the entire solution, which is 100 grams. That's the assumption we started off with. So if we use density, where is that 1.043 going to go? Is it going to go on the top or the bottom? Let's remind ourselves derived units and how to get inequality. That's helpful to us. 1.043 grams per milliliter or centimeter cubed means 1.043 grams is in 1 centimeter cubed or 1 milliliter, same thing. So now can you tell me, where does the 1.043 go? On the bottom, yeah, so 1.043 grams goes on the bottom. 1 milliliter goes up top, and then I'll go ahead and convert to liters by dividing by 100, and so we get that this solution, if we have 100 grams of it, there is 0.1043 liters of solution present, and this is the number that goes in our denominator, all right? So then putting these two values together that we calculated, the molarity of this solution is 0.02355 moles of solute over 0.1043 liters of solution. And then we get that molarity answer that's in the corner, 0.246 molarity. Right? So this question, I gave you the same information, but in order to calculate molarity, we did in fact need to use density here. And so again, being very, very careful of the units of these concentration units. Are we talking about just the solvent, just the solute, or are we talking about the solution as a whole? All right? Okay. So I will say that one, this one when calculating molarity is a little bit harder than the previous one because density is involved. Okay, so let's do another example. All right, let's calculate the molality of hydroxide ions dissolved in a solution where we combine 3.24 grams of barium hydroxide and we dissolve it in 258 grams of water. So I have it up here for you, the unit of molality. In this case, if we want molality of hydroxide ions, we need to figure out how many moles of hydroxide do we have and divide it by kilograms of water. Do we have any one of these already, basically? Yeah, we have the denominator, kilograms of water. I told you that there's 258 grams of water, so that denominator is going to be 0.258 kilograms of water. So we already have that one. So now we just need to calculate how many moles of hydroxide are present in this sample. So what information are we going to use here? Probably the other piece of information, yeah, that there is 3.24 grams of barium hydroxide in this solution. So if we start with 3.24 grams of barium hydroxide, so barium hydroxide has 1 barium cation and 2 hydroxide anions because barium is a 2+ cation. We can go ahead and use the molar mass that's given, that barium hydroxide weighs 171.34 grams for every 1 mole of barium hydroxide. So, you know, we can calculate this. Is this answer going to be our numerator? If we complete this calculation where we get this is a mole amount though, right? We don't put it in our numerator? What's wrong with this number? It's moles of barium hydroxide. Yeah, we want moles of hydroxide, so we have to do one more step here where we can say, oh yeah, for every 1 mole of barium hydroxide that we have, there are how many hydroxides? 2, yes, 2 moles of hydroxide. All right, so that's a small detail, but an important one. All right, so for every 1 unit of barium hydroxide we introduce to the solution, we actually get 2 hydroxides out, or 2 anions out. And so when you calculate this, there is 0.03782 moles of hydroxide present in this solution. So this is the number that goes into our numerator. So we can go ahead and calculate molality now where that 0.0378 mole amount, oh, there's a 2 there, of hydroxide is present in this solution from the gram amount of solute that I introduced divided by the kilogram amount of water that I mixed with this solute. And so divide that out and you get 0.147 molality of hydroxide. And again, using the unit, understanding the unit of the question that's given, the unit that the question asks really helps you determine what you need to calculate. We know how to calculate moles of stuff. We know how to convert grams to kilograms, but it's just putting it together in a way that matches what the unit actually asks for is the hardest part here. All right, and so in this example, it's this ×2 hydroxide that kind of elevated this question that makes it different than previous ones. All right, okay, so that's molality of hydroxide. So let's do this last one. Calculate the molality of sugar in an aqueous solution in which X, what does X mean? What is that? Mole fraction, yes, in which the mole fraction of sugar is 0.05, so 5% of the moles of this solution is sugar. So we're calculating the molality. So the strategy here when given a mole fraction of something, kind of like mass percentage. What did we do? What was the assumption we started off with when given mass percent? If I tell you like, 5% mass percent something, we assume 100 grams of sample. So it's the same idea here, except for mole fraction. Let's assume we have 1 mole of total sample, so 1 mole of solution. So if that's the case, if we have 1 mole of junk in this beaker, how much of that junk is sugar? If we have 1 mole of stuff. 0.05, yes, we have 0.05 moles of sugar, but then how much, or I guess I didn't even tell you, what's the solvent here? It's water because it's an aqueous solution. So then how much water do we have? 0.95 moles of water. Yes. Okay. So again, starting with that assumption helps us just start with amounts that we can then use to calculate. All right. So let's review what is the unit of molality. So the molality of sugar is equal to the mole amount of sugar divided by the kilogram amount of solvent we have. So in this case, it's water. Do we have one of these already? This time we have the numerator already. Yes. So how do you think we're going to calculate kilograms of water? We're going to take the mole amount of water we just got, convert it to grams, convert it to kilograms, and then that's going to be our denominator. So in this theoretical 1 mole of total sample, only 95 or 0.95 of that sample is water. All right, and so then we can use the molar mass of water. I didn't give it to you. The molar mass of water is like 18. It's like 18.02. I didn't give it to you. So 1 mole of water is 18 grams. And then go ahead and convert that into kilograms. And we get that this sample has 0.017119 kilograms of water present, where we took the mole amount of water, converted it to grams using molar mass, and then kilograms. And so this number is going to go into our molality calculation, but this time it's going to go in the denominator. All right, and so we can then put everything together and calculate molality is going to be 0.05 moles of sugar divided by 0.017119 kilograms of water, and we get something that this solution has a 2.9 molality of sugar. Let the units guide you in what to calculate. You know how to do mole conversions. You know how to convert gram amounts, right? But the units themselves tell you, what you actually need to do. Okay, so let's do, 2 more. Got another one. Okay. So yes, this one is, what is the mole fraction of chloride ions in a solution that is 1 molality, so that's a small m, it's not a mistake, of calcium chloride? And I give you molar masses. All right, so again, let's let the units guide us. We want to calculate mole fraction of chloride, so that means we need to calculate the mole amount of chloride present in the sample, and we need to divide by the total moles of stuff in this sample. So when we dissolve a strong electrolyte like calcium chloride, does this solution conduct electricity? Yes. Why does it conduct electricity? What are the ions that are present that conducts electricity? It's the calcium 2+ and the chloride minus ions that are present that conducts electricity. So let's think about the particle view of what calcium chloride, this solution looks like. Because there's a small detail here, the total moles. We need to think about everything that's in solution. All right, the total moles of everything in solution is equal to what? Obviously, moles of water. We need to figure out how many moles of water we have. But what else is in solution? You might be thinking, calcium chloride is in solution. But calcium chloride in water actually exists as calcium 2+ and chloride minus ions. So we actually need to calculate how many moles of calcium 2+ we have, and we need to calculate how many moles of chloride minus we have in the solution. Right? Those are the 3 things that are in solution. It's water, calcium 2+, and chloride minus. All of that is in solution. Let's get mole amounts of all of those, and we should be able to get that denominator. All right? Okay, so it seems like we only need to calculate 3 things. How many moles of water do we have? How many moles of calcium 2+ do we have? And how many moles of chloride do we have? So let's look at the unit that's given. We have 1 molality of calcium chloride. So let's rewrite that in a way that's kind of more useful to us. 1 molality means that there is 1 mole of calcium chloride dissolved in 1 kilogram of solvent. So in this case, it's water. So if we do that, if we write that unit out and start with the assumption, let's assume we start with 1 kilogram of solvent. So this solution, our solution contains, that we're working with, contains 1 kilogram of water, but what else is there? 1 mole of calcium chloride. So those are the 2 things that we combined to make this solution, a mole of the salt and a kilogram of water. So how do you think we can calculate moles of water? Just convert the kilogram amount to moles. So that one's easy enough. But this one's a little bit trickier. If we have 1 mole of salt, calcium chloride, how many moles of calcium 2+ do I have? If I have 1 mole of calcium 2+, so if 1 mole of this dissolves, how many moles of the cation do I have present in that solution? 1 mole. 1 mole. That's it. Okay, if I dissolve 1 mole of calcium 2+ in solution, how many moles of chloride are present? Is it also 1 mole? It is 2 moles. Yeah, look at this balanced chemical equation that I have. If I have 1 mole of this, I'm going to get 1 mole of this, calcium 2+, because there is just 1-to-1 stoichiometry there. But I'm going to get twice as much chloride out. So I have 1 mole of calcium 2+, but 2 moles of chloride minus. And so the only thing I really need to calculate here is, okay, let's convert that kilogram amount of water into a mole amount. So 1 kilogram of water is 100 grams of water. Water weighs 18.02 grams is 1 mole. And so we get that there is 1,000 divided by 18.02, 55.49 moles of water present in this sample. All right, so this value, along with those other mole amounts we got, is our denominator. All right, so all of those 3 values added up will be our denominator amount. And so if we go ahead and do this calculation and calculate the mole fraction of chloride ions in this solution, what number goes on top? The moles of chloride in this solution is what? 2. Yes, we already got it. So 2 moles of chloride are in this solution. But the denominator is going to be 50, I think I can do this in my head, 58.49 moles total. And that's coming from all of the components of the solution. And then we get a mole fraction of like 3% of this solution, of the particles in this solution are chloride ions. So the tricky part here in this question is that there's 3 different mole components because the solute is a strong electrolyte. It separates into a cation and an anion, and we have to account that, calcium chloride contributes 2 anions for every 1 formula unit of that salt. All right? But again, letting the unit guide you, understand that really we only had to calculate 3 different things, but putting them together in such a way is the difficult part here, understanding that this is a strong electrolyte. All right. Okay, so that was molality to mole fraction for a strong electrolyte solution. Okay, so let's do one last concentration example. And I'll say this is the hardest part of the chapter, navigating all these different concentration units. All right, so let's calculate the molality of a 12 big M ammonia solution that has this density. And I give you the molar mass of ammonia. Okay, so we are calculating molality this time. So molality is small m, this is not a mistake. So molality of an ammonia solution is going to be moles of what? Solute, but in this case, what is the solute? It's ammonia, so moles of NH3, so we need to figure out how many moles of NH3 we have. Over what? kilograms of water. So it's not just water divided by water. No, it's kilograms of water. Okay. All right, so we need to figure out those two things. So let's, again, start with a strategy. Let's look at the units of molarity. All right, so molarity has a unit of moles per liter. So if we want to rewrite that molarity unit into something that's useful for us, like we would use in dimensional analysis, what that means is that there are 12 moles of ammonia dissolved in 1 liter of solution. That's what that molarity value means. So if we assume we have 1 liter of solution, pretend we have 1 liter of solution, how many moles of ammonia are present? 12. Yes, 12. So we already have one of these numbers. Which one do we already have? We have the top one, yes. So we have that top value. We know that there are 12 moles of ammonia present in this 1 liter solution. Now the hard part is getting the denominator. All right, so if I have 1 liter of solution and I want to go to a gram amount, now I have to use density again. All right, so let's go ahead and convert that liter value. So 1,000 milliliters, 1 liter, same thing. 1,000 milliliters of solution, I'm going to use this density value. So there's 0.95 grams per centimeter cubed, or grams per milliliter. So the 0.95 number, is it going to go on the top or the bottom? If I'm already in the unit of milliliters, it's going to go on the top. Yeah, so 0.9519 grams of solution is equal to 1 milliliter, same thing as a centimeter cubed. So this solution weighs 951.9 grams. So does this number go in my denominator? No, what's the problem? Oh, it's a gram amount. Yeah, okay, Dr. Ann, I'll just convert it to 0.9519 kilograms of solution. Does that number go in my denominator? No, because what should go in your denominator? Kilograms of solvent, so in this case, water. All right, so this weight we just calculated, this is the weight of the entire solution. What does the solution mean? Solution means solvent plus solute. All right, so we just want the number that the solvent contributes, not the solute. So in order to figure out how much of my sample is solvent, just the water, I'm going to use the 12 moles of ammonia that I know this sample possesses. I'm going to figure out how much that weighs, and I'll subtract the two, right? So 12 moles of ammonia, I can figure out how much that weighs using the molar mass. 1 mole of ammonia is equal to 17.03 grams. And so that 12 moles of ammonia is equal to 204 grams of ammonia, right? So here's the mass of ammonia. Here's the mass of the solution. Do you see how we can get the mass of the solvent, of the water? All right, so the mass of the water, just the water, is equal to 951.9 grams minus 204.36 grams. All right, so this, the solvent, just the water, weighs 743.3 grams of water. And that's the number converted to kilograms will go into our denominator. All right. So that 700 number goes into our denominator, so let's go ahead and put it all together. 12 moles of ammonia goes on top. The kilogram amount of solvent is 0.7433 kilograms, and we get that the molality of this solution is about 16 molality. This question is trickier. All right? Because how many of you just wanted to stop right here and put it in the denominator, right here at the 900? A lot of you. But remember, when we use 1 liter of solution and the density of the solution, we get the mass of the solution. And the first thing that I mentioned when we started this part of the chapter was, remember, solution means solvent and solute. Molality only considers the mass of the solvent when we do this calculation. So we need to figure out how much our solute weighs, do that subtraction to figure out just the mass of water that's present in this solution. All right? Okay, so that one's definitely harder. We had to use density because molarity was involved. All right, so those are all of the different concentration units. If you come to office hours, we can do a lot more calculations. I can guarantee you there will be at least one or two of these on, probably just one, on the exam, but which one is it? Okay, so just to overview everything we just did in this section, all the different concentrations we looked at, mass percents, parts per million, parts per billion. I like to group these all together because they start with the fraction. You just multiply by the appropriate multiplier. But these three, mole fraction, molality, molarity, understanding that the units there and whether you're considering solute, solvent, or solution, very important there. All right, if there's anything you take away from this chapter is that when we refer to the solution, it means solute and solvent that are there. All right, and so a lot of students get tripped up with density. When is density important? Density is important when molarity is involved. And so I like to draw a map, okay, that all of these units are related to one another. Mass percentage, mole fraction, and molality. They all live on an island together. As long as you know the molar masses of your solvent and your solute, you can interconvert between those three units perfectly, and it's fine, right? For mass percentage, mole fraction, and molality. But molarity lives on a different island, where if you want to go between those two islands, you also need to know density, grams per milliliter, of your solution. All right? So yeah, if you want to go to molality to mole fraction, don't need density. You want to go to mass percent to molality, don't need density. But if you want to go to mole fraction to molarity, do you need density? Yes, you do. All right? So that's how I understand it in my head. If you want to go to molarity to mass percentage, do you need to know density? Yes, because they live on different islands. All right. Okay. Yes, so that's how I remember it. Okay, all right, so those are our different concentrations. We're gonna bring back molality in probably a couple minutes. Okay, so solutions. Today is a perfect example of behaviors of solutions. We know water, pure water, freezes at 0 degrees Celsius. We know it boils at 100 degrees Celsius. And so on the first day of class, I kind of proposed to you, well, what if we start dissolving junk in water? What if we dissolve sugar? What if we dissolve salt? In 1210, we looked at the conductivity of those things. We know sugar water does not conduct electricity. Salt water does. Those were some properties we looked at. But now we're going to go even further and look at additional properties that happen when you start dissolving junk in water. And so this is a broad topic called colligative properties. So these properties that we're going to study depend on the number of solute particles dissolved in solution. The more solute that's present in solution, the more these things happen. As you increase the concentration of solute, as you increase the concentration of solute, what happens is that the vapor pressure of your solution, of your water, of your solvent lowers. When you dissolve more junk in water, your boiling point elevates. As you dissolve more junk in water, your freezing point depresses, meaning the freezing point of the solution goes down. This is why we salt the roads in the wintertime. And also what happens when you dissolve junk in water is that you get changes in osmotic pressure across a semi-permeable membrane. Right? So these properties you have experienced in the past. Salting roads, right? Salting roads increases, when you put salt on the roads, it increases the concentration of salt in the water, and so it lowers your freezing point. Here's me, I make maple syrup in the early springtime, okay? Maple syrup comes from trees, but it doesn't come out as thick maple syrup, all right? So when you tap maple trees in the springtime, basically what looks like water comes out of trees. And it's just very, very slightly sugary, very slightly sugary. And so what you do to make maple syrup is you boil that water down to concentrate the sugar. And then what happens is when you get pure maple syrup, your boiling point temperature of that mixture increases. The boiling point temperature of maple syrup, and this is how I know when my maple syrup is done, is about 103 degrees Celsius. All right? I have an activity in the recitation packet for you to calculate the boiling point temperature of maple syrup for you. Okay, so let's explore these things and explain why it happens. Okay, so all of these ideas are related to one another, okay? And it is based upon what we call Raoult's law, where as we dissolve solute in water, we lower the vapor pressure. So let's remember what vapor pressure is for liquids. Just to remind you, liquids, yeah, so vapor pressure, it's expressed as a pressure. And you might be wondering, but you might be thinking, oh, but like liquids, they're a liquid, they're not a gas. But we should understand that, over time, many liquids evaporate over time, and that's due to vapor pressure. So for example, water, does it smell like anything? Does water smell like anything? No. Does nail polish remover smell like anything? Yes. So which one exerts a higher vapor pressure that your nose can sense? Nail polish remover, yeah, nail polish remover is like acetone, all right? And so it exerts a higher vapor pressure at room temperature. So when you have a liquid, the liquid and the vapor pressure and the gas phase are at equilibrium, and so the trends we talked about in 1210 were typically as temperature increases, vapor pressure increases for your sample, all right? A sample will boil when your vapor pressure is equal to atmospheric pressure, so one atmosphere. Also for different samples, the degree of intermolecular forces that are present in your sample is inversely related to vapor pressure. As particles are more attracted to one another in the liquid phase, they're not going to let their friends go to the gas phase. So usually those liquids exert a very low vapor pressure, so you can't sense the gases. Basically, these liquids are not smelly when there's a lot of intermolecular forces present. My analogy doesn't work all the time, but it does get us to start thinking about vapor pressures. Okay, so those are the trends from 1210 about liquids and their vapor pressures. Okay, so what happens when we start making a mixture? So if we think about just a pure liquid, all right, pure liquid, at equilibrium, meaning that you have your liquid at the bottom and its vapor pressure, particles in the air that it's smell, essentially, all right? That those are the particles, that's your vapor pressure of your liquid, and then that's the liquid. Let's think what happens when we dissolve stuff in that water. So let's say we dissolve some salt into that solution. So what happens is when you dissolve that salt, some of those salt particles or solute particles are at the surface of this liquid, and so what happens is that not as many solute particles go into, not as many solvent particles go into the gas phase to produce the vapor pressure that there was before. And so the presence of those particles lowers the vapor pressure of the pure water that it is mixed with. All right, so dissolving anything in water will lower the vapor pressure of water, and it follows Raoult's law, where Raoult's law says that the vapor pressure of your liquid is equal to the mole fraction of your liquid, of your mixture, of your solution, times the vapor pressure of the pure liquid. All right, so we're using mole fraction again. All right. So for example here, the partial pressure, the vapor pressure of water exerted in a mixture is equal to the mole fraction of water that's in that mixture times the vapor pressure of water in its pure form. So we're just using mole fraction here. Okay, so let's just think to ourselves, if we have a pure sample of water, what is the mole fraction of water present? What is it? If it's just pure water, what's the mole fraction of water in that sample? 1. Yes, it is 1. Perfectly 1. All right, a pure sample of water. So if you can even use Raoult's law for this, that if you have a pure sample of water, mole fraction of water is 1, and so the vapor pressure of that pure water sample is equal to what water typically has as its vapor pressure. But once we start dissolving stuff in water, how will mole fraction of water in a mixture change? How will this 1 number change? Is it going to go up or is it going to go down? Down. And so this is why you see when you dissolve stuff in water, vapor pressure is always lowered. Because as you dissolve stuff, mole fraction of water is going to go down. And so therefore, the actual observed measured vapor pressure of that water will go down as you start mixing salt or sugar in water. All right, so let's do a calculation. Okay, so glucose. So we're adding a non-volatile solute. So we're starting with water, we're adding a non-volatile solute, meaning that that solute does not contribute a vapor pressure in itself. So we are mixing glucose and water at 37 degrees Celsius. The vapor pressure of pure water is 47 torr. So let's calculate the vapor pressure of this solution when we mix glucose and water. All right, so if we had a pure sample of water, it would measure a vapor pressure of 47. But do we have a pure sample of water? No. So we need to calculate how much of this sample is actually water to calculate the extent of the vapor pressure lowering of this solution. So 47 torr, that number is this number right here, the vapor pressure of the solvent in the pure form. That's what that little knot means. So this number is 47.1, right? So we need to calculate how much of our solution in a mole fraction is actually water. So mole fraction of water in this case is equal to the mole amount of water over the mole amount of solution. What is my solution? What's in my solution? Moles of water and moles of sugar. Yes, so I need both moles of sugar or glucose, whatever, moles of water. Right? So it looks like we actually only need to calculate 2 things. Moles of water, moles of sugar. Do I have enough information to do that with the information given? Yes, because I have gram amounts. So let's convert 50 grams of glucose and 500 grams of water into mole amounts. So I give you the molar mass of glucose, so 180 grams is 1 mole of glucose, and then water is 18 grams, 1 mole. And so we see this sample is comprised of 0.277 moles. Oh no, my pen's dead. Come on. Moles of glucose and 27.7 moles of water. All right, so those are my mole amounts. So let's put together the mole fraction calculation here. So what number is going to go in the numerator? Which number? 27.7, all right. Then what goes in the denominator? 27.7 plus the other mole amount, yes. Sorry, I need to give my pen time to charge. Nope. We want moles of water here because this is mole fraction of water. So 27.7 moles of water over 27.7 plus the 0.277 value. And so we see that this solution is 99% water. That is mole fraction of water. Once we started dissolving solute in this solution, mole fraction went from 1 for water, and then now it's starting to go down. All right, wait, is this my answer? Nah. So to get the actual partial pressure or the vapor pressure of water of the sample, we need to take that 99% and multiply it by the vapor pressure of water in its pure form. So 0.99 times the 47.1 torr. All right, you can think, oh, only like 99% of the particles are water, so it's only going to exert 99% of the vapor pressure in its pure form. And so we get that the vapor pressure of this mixture when we added a non-volatile solvent or solute is 46.6 torr. Okay, so let's do a demo to demonstrate the vapor pressure lowering of water. As we add solute to a solution, as we add a solute to water, vapor pressure is lowered. So I have a demonstration here, okay, where I have two big beakers or two Erlenmeyers of pure water on each side. Okay, so this water is pure, this water is pure. So how do the vapor pressures of these two samples compare to one another? They're the same. Yes, they are the same vapor pressure. All right? So what I have here is these two containers are connected by some lines and a liquid. And so we have the liquid is colored, so you can see the levels of where the water level is. So if both of these containers are exerting the exact same vapor pressure, think this solution is pushing down on this side of the water level, this container is pushing on this side of the water level. If there's the exact same vapor pressure, how should the water level compare in this tube? Shouldn't they also be the same because they're both pushing down with the same pressure, all right? So what I'm going to do is knock over a little beaker of salt that's on the inside of one of the solutions. So when I make a salt solution on this side, what's going to happen to the vapor pressure of just this container? It's going to go down. Dissolving junk in water always makes the vapor pressure go down because we reduce the mole fraction of water that's in that sample. Right? So if I dissolve the salt in water, vapor pressure goes down. Predict how the water level, or not the water level, but this little indicator levels will change. Okay, let's see if this works. Last time I did this, it didn't work. So let's hope that everything works. Okay, so right now the indicator is equal because they're both pure water samples, but then if I knock over the salt in this one, what happened to the indicator level? We saw now it's going like this, all right? And so the indicator level is moving in this direction, so this beaker is now exerting a lower vapor pressure than the other one. So that's why the water level indicators are unequal, because we've lowered the vapor pressure in the saltwater solution while the pure water still remains the same, right? So dissolving stuff in water always lowers the vapor pressure, always, of our water. Okay, so there's the demo. Okay, and so in this case, water is the only thing that's contributing vapor pressure because we dissolved a solute that does not really have a vapor pressure like a solid. Salt, sugar, those things don't exert vapor pressures of their own. But let's consider, well, what if we mixed water, which has a vapor pressure, and another liquid that has a vapor pressure, like ethanol or something, right? So if two liquids that you're mixing both exert vapor pressures, we need to consider the vapor pressure of both of them, right? So we can extend Raoult's law and say, oh, component A, which is volatile, exerts a vapor pressure. Component B also exerts a vapor pressure. So to calculate the vapor pressure of a mixture where both components are volatile, we need to add those two components together. right? So in this example of using Raoult's law, we're just adding another component here, that the total vapor pressure of this system is equal to the mole fraction of component A times the vapor pressure in its pure form plus the mole fraction of B times its vapor pressure in the pure form. So we just have two components. I like to think of this kind of like weighted averages a little bit, where there's multiple components and you have to consider the percentages of both. But this time we're just using mole fraction instead of like percent abundances, right? So in this example, how it's different than our previous one is that both components exert a vapor pressure. All right, so let's do this calculation. So yes, okay, so at 63 degrees Celsius, so a little bit warmer, the vapor pressure of water is 175 torr. And the vapor pressure of ethanol at the same temperature is 400 torr. We make a solution by mixing 50 grams of water and 100 grams of ethanol. What is the vapor pressure of the mixture? So this time, both components are contributing vapor pressure. So you can think, okay, this component is water, this component is ethanol. So this question already gives you the P naughts, where this value, P naught A, this is your pure vapor pressure of water. So this number is 175 torr. And then PB naught, so the pure vapor pressure of ethanol in its pure form, this number is 400 torr. So basically our strategy is we need to figure out how much of this mixture is A in a mole fraction, how much of this mixture is B in a mole fraction, and then just use Raoult's law, multiply, add them up, all right? Okay, so how do you think we will calculate mole fraction? Convert, we are given the information in grams, so we got to convert everything to moles, calculate those mole fractions. So I am mixing 50 grams of water and 100 grams of ethanol, and I am nice and gave molar masses. So 18 grams of water is 1 mole. Ethanol, 46.07 grams is 1 mole. And so this sample contains 2.77 moles of water, and it contains 2.17 moles of ethanol. All right. So we have mole amounts of two different components. I'm going to just go ahead and calculate, okay, what are my total mole amounts of my two components of this mixture? So in total, I have 4.94 moles of stuff dissolved in this solution altogether. The solvent, the solute. I'm not sure which one's the solute and solvent, all right? But we have almost 5 moles of just stuff in this beaker. And that's useful to us because to get mole fraction of water, I'm going to take the 2.77 number we just calculated, but then divide by 4.94. To get the mole fraction of ethanol, I'm going to take 2.17 and divide by 4.94. All right? And so what we get is that this mixture is 0.561, so 56% water, and 0.439, so 44% ethanol. What's special about these two numbers that we just calculated, these two mole fractions? They should add up to 1. Yes, both these numbers should add up to 1 because those are the only two components I have. Okay. So those are my two mole fractions. And so if I use that mole fraction, multiply by the vapor pressures in their pure form, I can calculate what is the contribution of each of these solutes to the total vapor pressure. So the total vapor pressure of this solution is the 0.56, 56% of water, times 175 torr. So this is the contribution of water, plus the mole fraction of ethanol, so 439, that's of ethanol, times ethanol in its pure form, so 400 torr. All right, so just to clarify, this is Raoult's law for just water. This is Raoult's law for ethanol. And so since both of these components are volatile, I have to consider both of their vapor pressures. And so I won't skip this step. I'll tell you that water is contributing 98 torr, and then ethanol is contributing 175.6 torr. All right, so I just showed that multiplication, but then when you add up those two vapor pressures, you get a total vapor pressure of 273 torr, right? So we just did Raoult's law twice and added them up for a mixture where both of the components are volatile, right? So we need to use mole fractions of both of those volatile components and the vapor pressure of the pure substance. So this question differs than our sugar example, because does sugar exert a vapor pressure? It's a solid. No, it doesn't. So we only need to consider water because it does exert a vapor pressure. Right? So you can think in our sugar example, we're still kind of using this expression, but for sugar or salt, that this component is just very, very small or very close to zero, so we don't need to calculate it. We don't need to consider it for where your solute is a non-volatile component. Okay, so let's do another one that's it's very similar, but I ask it a little bit different way, and expands on what we just talked about. Let me actually go back to this question. So when we put all of these numbers together in Raoult's law, we see that water contributes 98 torr in the vapor phase. Ethanol contributes 175 torr in the vapor phase. So if we took this mixture and inspected the vapor above this solution, will the solution contain more, or sorry, will the vapor phase, based upon these numbers, will the vapor phase above the liquid contain more water particles or ethanol particles? Do you think? Water? Ethanol. Yes, it's ethanol. Why do you say ethanol? Ethanol contributes more vapor pressure in this addition. So there has to be more ethanol particles in the vapor phase. So let's inspect that, all right? Okay, so here I have another example, but with easier numbers. So we have A, there's pure A, there's pure B. Okay, so pure A is 126 torr, and pure B is 285 torr. So our strategy is the same here. We got the pure forms, so really what we need to just get for this question is, okay, what are the mole fractions of stuff when we mix A and B? Both of them are volatile, so we have to use this expanded Raoult's law, right? Okay, what is the mole fraction of A and B in the solution? So I'm mixing 0.78 moles of A, 0.22 moles of B. I tried to make these numbers really easy, because if you add up those two mole amounts, you get 1. So A, the mole fraction of A is equal to 0.780, and the mole fraction of B is equal to 0.220. I try to make the numbers easy this time, because N total is equal to 1. All right. So let's go ahead and calculate the total vapor pressure above the solution. So just like before, where we're going to insert these mole fractions into the equation along with the vapor pressures in their pure form. So I'm going to do it the same way. The total pressure is equal to the mole fraction of A, so 0.780, so 78% A times 126 torr. That's the pure vapor pressure of A, plus 22% B times its pure vapor pressure, 285 torr. Okay, before I even calculate this, tell me, based upon the composition of this solution, it's 78% A, 22% B. Will the total pressure of this mixture be closer to 126 torr or closer to 285 torr? Which one's it going to be closer to? 126, why? Because, yeah, there's more A, yeah. And so kind of like with weighted averages, since there's more A, the A component, that total pressure is going to be closer to A. All right, so I'm going to do this the same way. If you multiply those mole fractions together, you see that A contributes 98.28 torr, plus B is contributing 62.7 torr. So we see that the vapor pressure, the total vapor pressure above this mixture is equal to 161 torr. All right, and so we were right. Yeah, 161 is closer to 126 than it is to 285 because there's more A present in the liquid phase. All right, so we already know how to do that. This one is just review. But now the follow-up question is different. So in this first question, I asked, what are the mole fractions of A and B in the solution in the liquid phase? Now this third question, it looks similar to the first question, but it is different. What is the mole fraction of B, but in the vapor phase? In the vapor phase. So what a lot of students will want to report is this number right here. Oh, that's the mole fraction of B, but this is the mole fraction of B in what? In the liquid phase, yes. So to get the mole fraction of B in the vapor phase, or of A, if I know the vapor pressure that B is contributing, and divide it by the vapor pressure total, I can get the mole fraction of B in the vapor phase. And I actually have all of the numbers I need right here on this slide, right? I told you that A is contributing 98 torr, component B is contributing 62 torr, and I have the total vapor pressure right there. And so the mole fraction of B in the vapor phase is equal to 62.7 torr divided by 161 torr. And so we see in the vapor phase, B is actually present close to 39%. So we get a different number here, that more of the particles of B are actually present in the vapor phase than in the liquid phase. So the composition in the liquid and the vapor are actually, in fact, different because these two liquids have different vapor pressures. All right, what would the, so let's just for completeness, what would the vapor pressure, or sorry, the mole fraction of A be in the vapor phase? Yeah, it's that number minus, or 1 minus that number, but if we wanted to calculate it, how would we calculate it? It would be 98.28 or whatever divided by 161, and we would get just the remaining amount there, all right? So we're inspecting those vapors that are present in the vapor pressures from Raoult's law. All right, I got 2 minutes. There's one last slide in this section that I'm going to go over, all right? And that is deviations from Raoult's law, all right? So what we just calculated was using this equation, Raoult's law, where all we have to do is utilize the mole fractions of two components in a mixture, multiply them by their respective vapor pressures. So you can think of, okay, depending on how much A and B you have in your mixture, if you have pure A, you're going to be close to 126 torr. But if you have pure B, you're going to be close to 285 torr. And as you move along this line, you're just changing the ratio, the mole fraction of your mixture, right? But utilizing Raoult's law assumes that there's no interactions, no attractions between the particles themselves, and so that's where we get deviations from Raoult's law. But for the most part, we're going to just follow Raoult's law exactly, but I will point out when there are strong solute-solvent attractions, we actually do get a lowering, we observe a lower vapor pressure than what Raoult's law will predict. And I only mention this because there was an exam question about this like 2 years ago, and I didn't mention it. It's in your book, but I didn't mention it, so I have that slide here. When attractions are strong, what we observe is a slightly lower vapor pressure than what Raoult's law predicts. All right? Okay, so we'll finish up chapter 13 and start chapter 14 on Thursday.